Okay, so we're back and we're working on 4, and we're now determining whether a series is absolutely convergent, conditionally convergent, or divergent. Now, as I've said multiple times, the best thing for you to do when you're looking at these is to first see if it's absolutely convergent. Basically, if you just got rid of the negative and you just looked at it without any negatives, would this converge or not? So this -1 to the n minus 1 is kind of the alternating part, right? So let's forget about this. And let's just look at this series. Does this converge? Kind of feels like 1 over n squared, right? Feels like 1 over n squared. So we can write this all out. We're going to get 4n squared minus 4n plus 1. And it really doesn't matter, right? Because when it's n squared or 4n squared, we just know this is going to be 1/4. That's a non-zero constant. And a non-zero constant means that these two will converge and diverge together. This converges by the p-test, and therefore the series converges by the limit comparison test. Now, if this series converges, if there's no negatives at all, that means we know that it converges absolutely. You know more work to do. Folks, I always do that as my first step. I always say, hey, do I even need to think about the negatives? Sometimes you look at it and say, yeah, I do have to think about it. But other times, you can look at it right away and say, no. This is a great example where I look at this one right away, and I know it's not going to absolutely converge. The reason I know it's not going to absolutely converge is by the limit comparison test. I see n over n squared, and I immediately think n over n squared is just like 1 over n. And this is going to equal 1. And therefore, these two will converge or diverge together. This is the harmonic series, and it diverges. So therefore, this without, right, if I just did this without the negative whatsoever, right, this has to diverge with the harmonic series. They diverge together. So I know it cannot converge absolutely. The question is, can it converge conditionally? So now we have to think about this -1. And think about this. The -1 to the n minus 1. When you plug in 1, then you plug in 2, then you plug in 3. This is switching. It's switching from 1 to -1 to 1 to -1. So it's alternating. So this already meets the first requirement, because this is alternating signs, and this is always positive, so therefore the whole thing is going from positive to negative, positive to negative, so it's alternating signs each time. If I look, as this gets really, really big, as n gets really, really large, this gets large, but this gets large much faster. In fact, n squared, if you did like infinity squared or whatever, a million squared, this is far larger. So the limit as n approaching infinity of base of n does equal 0. And lastly, if we look each term, and when I say this, this is really not, this is like the absolute, I should write this, right, to be clear, the absolute value of each term, right? If you took out the negatives and you just looked at this term, as you go larger, as n gets bigger, is each term getting a little bit smaller. And it is because it's just like 1 over n in the long run, and 1 over n. You just think about 1 over 1,000, then 1 over 1,001, then 1 over 1,002. It keeps on getting smaller. So because all three of these are met, we know that the series conditionally converges. By the alternating series test. Folks, just to be clear, in order for you to prove something conditionally converges, you have to show that the alternating series test works, and when you take the absolute value of it, that function actually, that series actually diverges. So you have to show both. And since you have to show that the absolute value diverges in order to prove conditional convergence, that's why I always first look for absolute convergence. Like I'm going to do here, n squared over n to the fourth. You know what it feels like to me? N squared, it just feels like 1 over n squared, right? The degrees. What happens here, folks? Yeah, by the p-test, this converges. This limit equals 1. So therefore, by the limit comparison test, this converges. Oops, sorry, we don't need the negative. We're looking at the absolute value, but we're looking at what happens before you even contemplate the negatives. And if this converges, then we know that this converges absolutely. It's a lot faster, right? When you converge absolutely, it's a lot faster. You don't have to worry about the next part. This one looks fun. Well, I have a lot of factorials going on, so I'm going to, again, like I always do, the first thing I'm going to do is I'm going to forget about the negative 1. I'm just going to look at what happens when I just look at this part here, just this term. And I have factorials, I have exponentials. I'm going to go to the ratio test. And again, folks, I'm doing it without the negative 1. If you're wondering, could I do it with the negative 1? You could, because of this right here. It's not going to make a difference. This does get a little messy. I'm only going to write that out because I already did problem, what was it? E, right? Because I did 3E. If you don't understand where that came from, go look what I did for 3E, the previous video. Oops, that's actually wrong. I didn't really notice that was 2n plus 1. So now I feel tempted because it's not just like 3E. Just so you see clearly. This is going to get a little messy. I think I'm actually going to move this space down to the next page because it's going to get that big. Let me put you on hold for a second. So I just jumped forward and I took out these n plus 1 factorial squared to the n factorial, and I just wrote them separately so they're easy to see. Then I have 3 to the n plus 1 over 3 to the n. Now I have to worry about this 2n plus 1. And this 2n plus 1 is really 2n plus 2 plus 1. That's what's in the denominator. So when you have 2n plus 3 factorial, and then 2n plus 1 factorial, when you multiply by the reciprocal, it comes up into the numerator. Okay. I said this one was a challenge when I was assigning it. Now you see why. This is the n plus 1, right? The factorials. This just becomes 3. Now this becomes 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So I'm just going to write it like this. What's that going to equal? This is 1/2. This is 1/2. This is 3/4. And 3/4 is less than 1. Which means this converges. If I don't even think about the negatives, it converges. And therefore, if I don't have to even think about the negatives, and it converges, that means this series converges. Absolutely. All right, let's move on to 5. Turn the page. We're now thinking about the intervals of convergence. We're probably going to wind up doing a whole lot of ratio tests. These are power series. These are all kind of just different power series that we're going to be working with. Figuring out where they converge. And remember, we have 2 steps. Well, actually, it's really 3 steps. But the first step we have to think about is what's the actual interval? And then the next step we have to think about is, now that we have the interval, do the endpoints actually work? Do they converge at the endpoints? So we'll be doing a whole lot of ratio tests. And I'm hopefully going to do these correct. I'm going to try and jump to these so that I can kind of, without spending too much time writing out the a plus 1 term. I'm hoping I'm going to get the n plus 1 term and the nth term and the nth plus 1 term. It's a mouthful to say. It can get complicated to write out, so I think I'm doing these correct and they feel right. That's what you would get after. That's kind of like, instead of me writing out this step here, I jump straight to this step here. This is 1. N squared plus 2n plus 1 over n squared, when as n goes to infinity, is 1. So this is 1. This is 1/2, and this is x plus 2. So this is just going to equal x plus 2 over 2. We know this is less than 1. So that means x plus 2 is between 2 and negative 2. And therefore x is between 0 and negative 4. Okay, so now we have to test the endpoints, right? When we come over here, let's plug in negative 4, we're going to get n squared times, plug in negative 4. Negative 4 goes to here, we're going to get negative 4 plus 2. Negative 4 plus 2 is negative 2 to the n over 2 to the n. And then we're going to have, we plug in 0, we're going to get n squared times 0 plus 2 is 2 to the n. 2 to the n over 2 to the n is 1. So this just, folks, I mean, this is just this, right? And this is just the same thing with a negative 1 up front. And both of these are going to diverge by the nth term test or the divergence test, which says that the limit as n goes to infinity of the actual sequence isn't approaching 0. If it's not approaching 0, it must diverge. So that means that's our final answer. Neither negative 4 or 0 works. I was tempted to write them together, but I'll just keep it the way it is. Again, I'm going to write it out this way, kind of moving ahead one step. This is going to equal 1, this is going to equal x, this is going to equal a. So we're going to have, and therefore we know that xa is less than 1, less than negative 1, and therefore x is between 1 over e and negative 1 over e. Now what those endpoints? Well, let's plug them in. If you plug in 1 over e here, what do you get? Well, if we plug in 1 over e, we're just going to get 1 over e to the n times e to the n. That's just 1. Right? The x and the e effectively turn into just 1. This diverges because this is the harmonic series. It's the harmonic series. If you look at it, it's 1 plus 1/2 plus 2. So it's the harmonic series. What about this other guy? Plug in negative 1 over e. Well, negative 1 over e is going to become negative 1 over n. And this is converge because it's the alternating harmonic series. We've talked about that before, right? As it's alternating, it's going from positive to negative every term. It is approaching 0 as n goes to infinity, and with each subsequent n, it's getting smaller and smaller. So it meets all three criteria to converge by the alternate series test. It converges conditionally because it's alternating. Here's where they get a little bit more challenging. This n plus 1 throws some people off. And most people, these ratio tests now we've kind of gotten down, hopefully, right? We're now just looking at the negative ones are relevant because of the absolute value, folks. You may say, why did you put the negative 1 in there? It just doesn't matter. Put the negative 1 into an absolute value, it doesn't really matter what happens to it. It just, when you take the absolute value of it, it goes away. Two times the quantity n plus 1 becomes 2n plus 3. It doesn't make a huge difference because this limit is still 1. Therefore, we just are left with the absolute value of x, which is less than 1. So therefore, we know x is less than 1 and less than negative 1. Now we have to plug in 1 and plug in negative 1. Here's where it gets a little bit uglier, and I've shown you a few like this before. When you come in here, you plug in negative 1, it gets a little messy. This is the endpoint, x is equals negative 1. For x equals 1, it's actually a little cleaner. Because you just get a 1 here, so literally this stays here. And this is going to converge by the alternating series. It's going to conditionally converge. Because it alternates as n gets bigger, the term's approaching 0, and as it eventually, the magnitude of the nth plus 1 term is smaller than the n. So it conditionally converges, so that means we can come up here and put a little sign here, but this one gets a little ugly. The top gets a little ugly because what happens is you get negative 1 to the 2n plus 1. And this negative 1 to the 2n plus 1, I know I've showed you this a couple times before, so if we have to do it again, I'm not going to keep on doing it. But this turns into that. And therefore, this is just 1. This is just 1 to the end. So this is just negative 1. So this whole thing is a fancy thing for negative 1. And it's actually not alternating. And since it's not alternating, they can only either absolutely converge or diverge. And if you look at this, if you do the limit comparison test with 1 over n, you will see it diverges. So therefore, x equals negative 1 diverges, x equals 1 conditionally converges, which is why that's our final. Moving on to D. I just want you to know, I want you to kind of start thinking about some instincts real quick, because they sometimes help to think about the instincts. Here you had n squared over 2 to the n. The 2 to the n went into here. You had like n squared in the numerator. And n squared in the numerator, when it was left, right, when at the endpoints, left you with something where it was getting really, really big and diverged. Here, when you had the endpoints, you had, you're always going to kind of have 1 or negative 1, right? And here, when you have 1 and negative 1 over n plus 1, you kind of get to that harmonic series. And that harmonic series is the one where if it's alternating, we have conditional convergence. If it's not alternating, we have divergence. So when it's like 1 over n, we know it's has to be alternating in order for it to converge. Here we had something on the order of 1 over n, and it too had only one. Oh, I forgot this, didn't I? This converged. I'm sorry, I forgot this, folks. Some of you were like, what happened? Sorry about that. So this one here, I want you to get the instinct of, well, this is, I'm betting it's like 1 over n squared. My instincts are, folks, that 1 over n squared is going to converge no matter what. I think that both endpoints are going to work. Let's see if my instincts are correct. Again, I'm always forgetting the negative because of the absolute value. I get 2x to the n plus 3 over 2x to the n plus 2 times, this gets a little bit sloppy, I just noticed another mistake from earlier. I'm kind of glossing over mistakes sometimes, and I apologize, folks. This up here was wrong. This should have been plus 3. That should have been plus 1. I mean, you may say to yourself, wow, aren't those big mistakes? Aren't they costly? No, we're seeing how it's not costly, right? We're seeing how they're of the same order of magnitude. Every time these are going to 1, and I almost made the same mistake here, but this is just going to 1. So even if I had this in the numerator and not in the denominator, it wouldn't have made a huge difference in the grand scheme. And this is really what matters, right? So we know that 2x must be less than 1. And therefore we have this as our limits. Okay, so now we have to test 1/2 and negative 1/2. So we come in to do 1/2 and negative 1/2. We come into here. And you plug in 1/2. Okay, you plug in 1/2, you're going to get 1 here. So it's just going to be 1 to the n plus 2, which is just 1, right? So we don't have to worry about this, right? It's just 1. And this is going to converge. I mean, not because it's alternating, but it's going to converge absolutely because 1 over n squared plus n, by the limit comparison test, with 1 over n squared. Right? You put 1 over n squared plus n over 1 over n squared. You take the limit of that. You're going to get 1, which is a non-zero constant. So therefore, they're going to converge together. Right? So this converges by the p-tests. Therefore, this is going to converge. So this converges absolutely. Which means when you come over here and you plug in negative 1/2, you're going to say, well, that makes a huge difference, right? Well, yeah, now you have negative 1 to the n plus 2. It really doesn't make a difference because if this converged absolutely, this is going to converge too, regardless of whether this is positive or negative. This is also going to converge. You could say to yourself, well, what if this was negative 1? It doesn't make a difference. If this is converging absolutely, this will too, because these are just some negatives with over 1 over n. So these are both going to converge. So this converges absolutely. And therefore they both converge. Both endpoints, they both work. Again, the instinct, something over n squared plus n, that's going to converge. So therefore both endpoints are going to converge. These are just instincts that are worth developing. Oh, and now my instincts here. N factorial just kind of trumped, right? N factorial is like a trump card. It comes in, for those of you that play Pinochle, trump card just kind of says, wow, I override everything. And exponential functions are usually dominant, but factorials just override everything. So you're going to come in here and you're going to say, well, okay. What do you mean by override everything? X to the n plus 1 over x to the n plus 1 factorial over n. Sorry, I did it again, and this actually does make a difference. Because I've made this mistake enough times, I guess it helps for me to show what I'm supposed to be doing. This is the n plus 1 term. I'm just divided here by the nth term. And instead of dividing by the nth term, what I'm just doing is I'm multiplying it by the reciprocal. Which is literally, folks, that flipped. That's a sub n. This is a sub n plus 1. I'm just multiplying it by the reciprocal of a sub n. I'm just flipping that term. And then what I do is I just reorder it so it's easier to see. And I've made that mistake enough times for me to kind of show you what I'm doing. And maybe you'll notice why it's easy to make that mistake. Why sometimes it might help for you to actually take that step out. Because here it does make a huge difference. I'm going to take a second to write this out this way. What does that equal? Well, x is some number. It could be 1,000,000, it could be 80, it could be 5, it could be 4. N plus 1, though, is getting really, really large. So this is going to equal 0, regardless of what x is. You could say, what if x was infinity? X is an infinity. X is a number. X can't be infinity because, it's a number. We didn't talk about x going to infinity here. So x is some number, and I don't care how large of a number you choose. No matter what, this is going to go to infinity. And if this goes to infinity, some number over infinity is going to be 0. And that's going to be always less than 1. So as long as x is less than infinity, as long as it's some number, it's going to converge. And that means for all x, this converges. The way we write for interval notation is we'd say it's in this interval. And so basically for all x, the interval of convergence is this, negative infinity to infinity. And then last, our fun one, the challenge one, the one that you should only be doing if you're in the mood to kind of push the envelope. So now we're going to come over here, we're going to say, all right, we have n plus 1 factorial, 3 to the n plus 2 times x to the n plus 1 times the reciprocal of this, which is just be flipping it. Okay, so what does that leave us with? The n plus 1 over the n goes to n plus 1. The x to the x to the n plus 1 over x goes to x. And the 3 to the n plus 1 over n goes to 3. Okay, we want this to equal 1. Well, this is going to infinity, folks. So you made yourself, no matter what, this is infinity. There's no possible way this could ever converge. And you're right, because this is going to infinity. No matter what number you put in here, this is going to be infinity times some number, right? So this is never going to be less than 1. This is always getting really, really, really large. So no matter what, this never converges. So this is going to always diverge. And it's tempting just to stop there and say, yeah, it makes sense. There's one small thing you have to remember. The one small thing you have to remember is that that always works when you have infinity times a number, right? The limit of infinity times some number is infinity. But we talked about, and I know I'm using shorthand here, that's not appropriate, but we talked about how this was one of our indeterminate forms, right? When we had this, when we had infinity times 0, this was one of our indeterminate forms. And before you walk away from this problem, just make sure that you have to, well, what happens if this is infinity times 0? Well, if this is infinity times 0, it's indeterminate. You don't know what this actually is. Maybe this would be 2. Maybe this would be 5. We don't know. We have to go way back to here and then figure out what would this be. If x was 0, what would this be? Well, what would the serials look like, folks? If you start writing them all out, what are you going to get? Oh, you're going to get n factorial times 0. You can start writing out 1. We start at 0. 1 times 0 over 3. So it's going to be 0 plus what? We'll plug in 1. 1 factorial of 0 over 9. Right? 0. 0. So this actually will converge at x equals 0. And this could be a really weird type of problem where there isn't really an interval of convergence. It just converges at a point. It converges at a point because if you start thinking about the series when n equals 0, you'll see that indeed the series is just 0 plus 0 plus 0 plus 0 plus 0 plus 0 all the way up. So it does technically converge at x equals 0. Again, like I said, that was a challenge problem, not something that you should be doing in your free time unless you're really in the mood. All right, folks, I'm going to take another break. Come back to finish up 6 through 9.